Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/Linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host, as usual, is Tobias Macey, and today I'm interviewing Dylan Fox about the challenges of training and deploying large models for automated speech recognition. So, Dylan, can you start by introducing yourself?
Yeah, I'd be happy to. So, as you said, my name is Dylan. I'm the founder of a company called Assembly AI, and we make an API for accurate and fast automatic speech recognition.
For people who didn't listen to the previous interview that you did talking more about the Assembly product, can you remind us how you first got introduced to Python?
Yeah, definitely. So I started learning how to program back when I was in college, and I started attending some programming meetups. Those turned out to be Python meetups, but I did not know at the time, and just got into Python, got into Django, and really that's where it all got started. So just made great use. I think, the website I learned Python on was called learnpythonthehardway.com. Have you heard about that?
Yeah, I have come across that one. I think it's from Zed Shah, I believe.
Yeah, I forgot that that's how I learned because it's a long time ago. But that is how I got started with Python. I mean, I'd always played around with computers, and I talked about this in the last podcast, was really into gaming as a kid. So would be on IRC all the time and made like websites in HTML and CSS, but never did any like software development until I was a little bit older. And I had bought a book about learning PHP and MySQL, this like huge textbook, and made it like halfway through and was like, okay, I can't do this. And then like maybe a year later, got back into it. And that's when I focused on learning Python. And it was much easier than PHP and MySQL.
Yeah, it's definitely interesting because I've had a number of people who have come on the show who used PHP as the entry point to programming and then got sick of writing PHP, and that was their entry to Python.
Yeah. You're having to learn so many new abstractions when you learn how to program. And when you also have to learn like a clunky syntax and the environment's more complicated, it just makes it a lot harder. So I think it must be why a lot of people are just starting with Python and Node as well, because it's just a lot easier to get up and running and get started.
In terms of the work that you're doing at Assembly, that's entirely oriented around automated speech recognition. And so there's a lot of machine learning involved, a lot of model training and development. And so for people who are sort of unfamiliar with that overall space and some of the complexities that are involved, can you just give a bit of an overview about what's actually involved in building an automated speech recognition model? And for the sake of brevity for the rest of the podcast, I'll just say ASR.
ASR, yeah. A lot of acronyms. STT, ASR. We can use ASR for now. What is involved? A lot of pain is involved. No. So I think with most machine learning projects, it's fairly easy to get to something that works reasonably well, but it's very difficult to get a machine learning model working state of the art and extremely well. The last 10% of accuracy seems to be where most of the work is done. Like you could probably easily go online and fork deep speech or wave to letter and get something up and running that is like maybe 70 or 75% accurate for speech recognition. But the real work is in how do you get it to be state of the art, which is like, 90% accurate on audio files. And there's so many different speakers, so many different accents. There's background artifacts like babies crying or noise, the sync being on. So it is a very challenging machine learning problem because the data is high dimensional. There's a lot of noise and disturbances in the data. So it's a pretty hard machine learning problem. And especially in that last rung of accuracy, that's where a lot of the work ends up being, is what we found.
In terms of just the overall machine learning space, there are a lot of other categories of data that people are going to work with, where there might be other applications of machine learning running on audio data that isn't necessarily oriented around the speech aspect. There are things around computer vision and being able to do object detection and object recognition, natural language processing, named entity recognition. What are some of the sort of distinguishing factors of ASR as compared to some of those other avenues of machine learning and deep learning in terms of the complexity or difficulty that's involved in actually being able to gain high levels of accuracy?
Yeah, it's a really good question. So let's just focus on NLP related tasks, NLU related tasks. Compared to speech recognition, compared to ASR, those NLP tasks tend to be a little bit on the easier side. And I think big reason is because you can piggyback off of these huge models like BERT, or you see this now with GPT-3. There's these huge models that you can piggyback off of to build a model that is more specific or tailored to the NLP task or NLU task that you want to build. And you usually don't need as much data as compared to ASR, and the data is not as high dimensional as with ASR. So with ASR, you have high dimensional long sequences of data that you're sending into your neural network. So the models end up being really big. And this gets complicated because now, there's huge NLP models like GPT-3. I was just looking into this. Like if you were to try to train GPT-3 on a single NVIDIA GPU, it would take like hundreds of years. And they actually trained that GPT-3 model on a huge cluster of V100, NVIDIA V100s that were, I think, donated or set up from Microsoft. And it took about 34 days on like 1,000 or more V100 GPUs to train GPT-3. So that is definitely the exception. Like in general, I think what you see is NLP models that are just working off of text tend to be smaller and tend to train faster and tend to just be easier to train and to get working reasonably well. I think it's also because there's just like a ton of text everywhere on the internet, online, that you can quickly get as training data to train these models as well. So for ASR models, you have high sequential data, or high dimensional data rather, that is a long sequence. And so you end up having these really big models that take a long time to train, that are also very compute intense to train. And so if you're going to try to train, like a 500 million parameter ASR model on tens of thousands of hours of data, you're going to need at least a dozen or more GPUs to train that on. So you're going to have to set up a way to train your models in a distributed fashion. And still, training is going to take a while. So iteration speed is slow and it's going to be expensive for inference. So it's just a more compute intense problem than other NLP or NLU problems. And that makes it just a lot harder to build these models.
So are you regretting your life choices that this is the particular area that you decided to build your business around?
Well, we have some NLP-based features that we offer now. So one, for example, with our APIs, we can detect key phrases and key words within the transcription text. And compared to the ASR models, like that's a fairly easy thing for our team to build. And that's because we have all this GPU training infrastructure set up, and we have these data pipelines set up, and we have capable people on the team. So it's still on its own a challenging problem, but compared to the ASR problem, it's like a lot easier for our team to build. And I think that we didn't fully grasp just how challenging ASR models are to build when we first started the company. I mean, the first 2 years of the company was really just training models, setting up infrastructure, getting more data, and getting the models to the point where they were state of the art. And it goes back to what I was saying in the beginning. Like, it's fairly easy to get something working reasonably well, but it's really difficult to get it working to a state of the art degree where you have an ASR model that is generalizable to many different types of speakers, to many different types of accents. It can handle background noise. It can handle channel disturbances. It can handle echo and reverberation. Like, that's very difficult. You need lots of data. You need a big model that can learn from all of that data And yeah, there's just a lot that goes into it. So I think now I don't regret it because, it's obviously like a barrier to entry because it's so difficult to things working this well, but definitely was challenging. And I think it's probably more similar to computer vision because computer vision, is also, high dimensional data. But the thing about computer vision, which is nice, is that most of the computer vision models are like convolutional neural networks that are less compute intense compared to with transcription with ASR models. You're using either like recurrent neural networks, you're using transformers, and those models are more compute intense and they take longer to train, they're more expensive to run, they're more expensive to train. So it definitely is one of the more challenging machine learning tasks.
As far as the accuracy and capabilities of automated speech recognition, and I'm wondering if you can talk through some of the ways that it has evolved as far as the capabilities and the particular areas of focus and utility over the past 5, 10, 15 years. Because I know that, there's the CMU Sphinx project that's been around for a long time that a lot of systems will use as sort of like a wake word detector that, obviously is a small model and, very limited in capacity, but, there are a lot of speech recognition systems that are being used for much more sort of long-running processes. Obviously, what you're building in assembly for transcription capabilities, and then systems such as these voice-activated assistants, such as the Amazon and Google devices.
Yeah. Have you used the CMU Sphinx package before?
A little bit, yeah. So I've experimented with the Mycroft project, and I know that they use the Pocket Sphinx for the wake word detector.
Yeah, we actually have someone on our team who used to work on the Mycroft project. So CMU Sphinx was actually one of the first speech recognition toolkits that I played around with years ago when I was first getting into the field as well. CMU Sphinx and Caldi are probably two of the more like popular traditional research frameworks. And there's a lot of opinions around Caldi. So it's almost like if you say something about it, you could get in trouble with the community, but that's been around for a while. So I think one of the complicated things from the outside looking in with the field of ASR is that like all the use cases that you spoke about kind of all get bundled in together, so like wake word detection versus like utterance detection for like to like an Alexa, or the like large vocabulary speech recognition. If you're trying to transcribe like a podcast like this, they all kind of get bundled in together to just like ASR, but there are different models behind each use case. And the technology's just gotten better, a lot better over the last couple of years. So like a long time ago, speech recognition models were built with like the GMM, HMM architecture setup. So like Gaussian mixture models and hidden Markov models. And the accuracy was not very good. And those are the models that CMU Sphinx was based on top of. It was decent, but it was not very good. And so what people used to do is they used to just customize the crap out of those networks. They used to like adapt them basically to their specific use case and domain. So like if you only need to recognize like these 20 words, you can think of speech recognition as a search problem. And if you limit the vocabulary to just those 20 words, it all of a sudden becomes much, much easier. So if you're trying to build just a simple like hands-free device in your car, you could probably get decent accuracy with the very simple like GMM, HMM model that just has a very limited vocabulary of like 5 words. And CMU Sphinx was like a pretty easily accessible toolkit for speech recognition that allowed you to build pretty simple GMM, HMM models. But what started happening is GMM part of the GMM, HMM models started to get replaced with deep neural networks. So that part of the modeling started to become a lot more powerful and more accurate. And then kind of just fast forwarding a bit, there was that deep speech paper that came out. Did you read that paper? Are you aware of that paper from I think it was Baidu that put it out?
I've heard of it, but I haven't read it. So
yeah, actually, I'm not sure if it was Baidu or NVIDIA. I think it might have been Baidu. I'm getting mixed up now. But they popularized one of the first end-to-end deep learning speech recognition architectures. Tell me if I'm getting too much in the weeds here. But like most traditional speech recognition architectures, they work by predicting phonemes. So you take your training data, you convert it into phonemes, and then you're basically training a model to predict phonemes over time. And so you have to do this step called forced alignment. So you're basically saying like at this millisecond, they're saying this phoneme. And then you're trying to predict what phoneme is spoken over time. And then once you get your phonemes out, you take it through another process that tries to actually convert those phonemes into words. And so it's like this very complicated setup. And even from a training perspective, It's complicated because you have to convert your words into phonemes. That's a lossy process. You have to align the phonemes with when they're being spoken. That's a lossy process. And then on the other end, once you get your phonetic predictions out, you have to try to map them back into words. And that's a lossy process. So there's like a lot of steps. And what the deep speech paper showed, which really popularized, was a fully end-to-end. And when people say like end-to-end speech recognition, like this is what they mean. You're sending in audio and you're getting out graphemes, you're getting out characters. You could take the most probable character over time and directly out of the neural network, and you could just get a transcription. And so deep speech really popularized the move in that direction. And since then, end-to-end speech recognition architectures have gotten a lot more powerful, especially with the advancements that have come out with transformer-based neural network architectures. There's been improved loss functions that have come out since the original deep speech paper. So deep speech was trained with a loss function called CTC. And the CTC loss function, there's some flaws in that. It's really amazing what the inventor, was able to come up with. But there's some flaws in that loss function. And there's been some new loss functions that have come out that have allowed for these models to be even more accurate, these end-to-end models to be more accurate. What's nice about these advances in these newer end-to-end deep learning-based architectures is that the GMM, HMM, more traditional old school ASR architectures, they had kind of plateaued. So even if you were to throw like 10x more data at them, you weren't really going to see an accuracy improvement. With the newer neural network architectures that have come out, the end-to-end based architecture. So a few of the popular ones, there's deep speech, there's wave to letter, there's RNNTs. They're able to learn from a lot more data. So, if you throw like 100,000 hours of training data at those models, they're going to learn a lot. And not only is the modeling power behind those models better, but they're also able to generalize better because they're just seeing tons of data. And so long story short, the accuracy for all these reasons has just gotten a lot better over the last 10, 15 years. Even over the last 5 years, the accuracy has gotten a lot better. So like when we started the company compared to now, even our accuracy has improved like 30, 35% relative. So it's just gotten a lot better. And technology is just getting a lot better. And there's a lot of advances that are coming out and new research that's coming out all the time. And that's why you see applications popping up now that probably weren't really possible like 5 years ago, even around Zoom meeting transcription or phone call transcription, video transcription. There's a lot more possibilities now that the tech is more accurate. A great example of that is the Alexa and the smart speakers. Like those would not be possible like without deep learning models powering them. It just wouldn't be accurate enough to be usable by consumers.
Another interesting aspect of this space is that speech recognition isn't the only use of audio data for machine learning contexts. One of the interesting conversations I had on the data engineering podcast was with a company that was working on collecting all kinds of different sounds and noises that you might encounter to be able to do noise recognition or sound recognition, where you want to be able to, in a security context, identify the sound of breaking glass, or in the sound of sort of industrial automation, you want to be able to understand what are the sounds that a machine is going to make that are predictive of a breakdown so that you can do preventive maintenance. And I'm wondering if you can just provide some context as to some of the differences that come up of needing to be able to understand the peculiarities of human speech in these waveforms versus some of the other ways that sound data might be used in a machine learning context.
Yeah, I actually have a Google Nest Home, whatever those little devices are in my kitchen, and it went off the other day and it was like broken glass detected. So they must have one of these models locally running on their device, which is maybe privacy invasive, but that's another discussion. Yeah, there's a lot of applications happening around like emotion detection, noise detection. Motion detection is an interesting one. A lot of people will try to do sentiment analysis on top of transcription text, and that works reasonably well. But being able to detect emotion actually within the audio is way more accurate than trying to do sentiment analysis on top of the text that's transcribed. Another field that's really interesting is source separation. So are you familiar with source separation at all?
Sounds like being able to extract the different audio sources from, maybe a mono recording file.
Yeah, exactly. So if you have like 4 speakers in a file, you can basically create like 4 unique audio files, each with, one speaker in there because you can do source separation. And that's really cool technology because if you can basically remove a lot of crosstalk, which if you have a single file with 4 people talking over each other and you have a lot of crosstalk, that makes it a lot harder for speech recognition models. That makes it a lot harder for any other model that might be modeling that data. But if you can separate out the speakers, and this is different than speaker diarization. Speaker diarization is basically, a model that can tell you like, hey, we identify there's like 4 speakers in this audio file, and speaker 1 spoke at this time and speaker 2 spoke at this time. So you could use speaker diarization technology to do something similar, but source separation, it's just more advanced. It's just a different application. So source separation is personally something that I'm more interested in, and it's something that we're looking into, but it's pretty complicated stuff. I think most deep learning research has been around like computer vision and NLP, and there hasn't been that much research around speech. It's been not as popular as computer vision research or NLP research. And I think that's because the models are harder to train and you need more data, and data is hard to come by. But I think that's starting to pick up, especially, with companies like us. We're putting out our own research. We're really pushing the boundaries of what these models can do as well. Yeah.
Digging into some of the technical aspects of ASR model development and management and deployment, you mentioned how the size of the model is a factor when determining how you want to go about training the model and some of the complexities that arise around working with it as compared to maybe an NLP model. And I'm wondering if you can talk about, just give some sort of general orders of magnitude about the type of size that we're talking about in terms of the model and some of the contributing factors that will influence the total size of a model in terms of the different applications and how that plays out as far as being able to deploy and manage and sort of retrain them.
Yeah. So in general, bigger is better. And the bigger the models you train in general, the better performance. We've actually done some experiments where we'll have a pretty simple neural network architecture, and then we'll have a pretty advanced neural network architecture. And if you make both models like 50 million parameters, for example, and you train on a data set, the more advanced one, will perform noticeably better. But if you then make them both like 500 million parameters, they end up being a lot closer in performance, because even a simple model, if you just make it like big enough and you train it on enough data, you can actually get like pretty good performance. So it is kind of interesting how like the bigger you make your model and the more data that you throw at it, the less the actual like model architecture matters. But that is not always the case, as shown with things like transformers being, much better than recurrent neural networks for sequential data. But to your question, training large models is difficult for a number of reasons, and some that are unique to startups, which I don't know how much we want to get into that, but like just for one reason, that if you have a really large neural network, sometimes you can't even fit that entire neural network on a single GPU. When you're training, you have to train different layers on different GPUs, or sometimes even train different layers entirely on different machines, because there's only so much memory that each GPU card has. And you might not be able to like fit the entire training time onto a GPU. And so if you get to a big enough size, then you have to start doing distributed training. And distributed training has a lot of complexity that goes into it, because one, there's a lot of just software development that has to go into doing distributed training well. And there are some nice libraries out there. Like one is from Uber. It's called Horavad. And we've been using that for a while. And that works pretty well for efficient distributed training of large models. But like as you add more machines to your training cluster, you don't always get a linear performance improvement. And these machines are super expensive. So you can't just go from like 1 to 10 and get a 10x speed up. You might go from 1 to 10 and get like a 6x speed up, and then like 10 to 20 and get like a 7x speed up. Because once you start communicating and having to like communicate large tensors and a lot of data between machines, there's network overhead, and it can just get complicated really quickly. So there's a lot of work that goes into setting up a training infrastructure that can train large models fast and without it costing a ton of money. Because at a startup, you're trying to always optimize for like speed and time. And if your models take like 6 weeks to train, Like for a startup, that's eternity. And you want to try to iterate much faster than that, because a normal startup can like go collect feedback from customers and then, overnight, like ship a new feature if they're just building like a CRUD application or something. But when you have to train models and those models take weeks to train, you might find out 6 weeks later that you made a mistake or that your model's actually not better. And then you have to go back to the drawing board and train again. And before you know it, like months can pass by, and you just don't have that kind of time as a startup. So the way to get around that then is, all right, well, let's train on more compute. But more compute is expensive. And as a startup, you may not always have a huge budget to throw at compute. So there's just a lot of complexity that goes into it and a lot of factors that go into it. From a training perspective, definitely like my advice to companies training large models is always like, don't do it on the big cloud platforms like AWS or Google Cloud. It's crazy expensive, and you can do it much cheaper if you buy dedicated hardware, even like rent dedicated hardware from other providers, or even if you just try to buy your own training, like it'll just be much, much cheaper. But I will say the landscape has changed since when we started the company. So when we started the company, we were training models on like NVIDIA K80s, which are so slow compared to the V100s or A100s that are out there now. It's like insane how much faster they are now, especially if you optimize your training and your network to perform really well on the new NVIDIA cards, like the V100s and A100s. So it's a very long-winded answer to your question of that, like, it's just complicated to train large models. And this goes back to one of your earlier questions of like, how is it different from NLP? Like you can train pretty advanced NLP models on a single GPU that work really well. And so, and it may take like 3 days to train, which is not going to break the bank. And 3 days is like no time. But if you have a really large ASR model that takes like 6 weeks to train on like 42 GPUs, that all of a sudden is a lot of money and a lot of time. That's from the training perspective. So there's a lot there we could keep talking about, but like from an inference perspective, it does get easier because there's a lot you can do to prune large models. You can quantize large models to make them faster for inference and take up less memory footprint. There's also techniques like knowledge distillation, which I don't know how familiar you are with that, but you can like squeeze a larger model like into a smaller model basically. So you have a smaller model like learn the behavior of a larger model, and you're able to like distill knowledge into a smaller network that you can use at inference time. So inference is actually relatively not that challenging. On its own, it is challenging. Like any given day, we're maybe running like 100, 150 GPUs in production for inference because we transcribe millions of audio files a day with our API. But it's a beast. I mean, all this is kind of going back to it's just a beast. And, I remember when we were going through Y Combinator, there were some people at OpenAI that were making themselves available to like advise the YC AI companies. I was explaining to them what we were doing and like our models and our data and everything. And they were like, wow, okay, this is like, pretty advanced stuff and like high compute stuff that you guys are doing. And I think, most like AI startups are actually not doing that high compute or like large scale model training. Like it's pretty rare that a company our size is pulling off training models like this big for this challenging of a task. Yeah, it is kind of like you can't just like Google the answer. You have to really figure this stuff out. How do you do this? It's been a beast though.
As far as the actual like size of the model specifically, just in terms of like space on disk or space in memory, like what are some of the sort of comparative sizes that you're dealing with from some of the models that you're building versus the, size of a simple NLP model that somebody might train from scratch?
Well, let me do the math really quick. Like some of our training machines, for example, they have 16 NVIDIA V100s. Each NVIDIA V100 has 32 gigabytes of memory. So it's 512 gigabytes of memory per machine. And we're training our models on like multiple machines. So from a training perspective, it's like, 1024. We get like reasonable training turnaround time on like 32 to 42 V100s. So you're talking, each GPU times 32 gigabytes of memory to get like the total like GPU memory requirement is. From a training perspective. From an inference perspective, it's a lot smaller. Like, so we deploy some of our inference workloads into AWS cloud resources. And I believe we use the NVIDIA T4, which is like the G40N instance class, I think. That has I think like a 15 gigabyte GPU memory footprint. And, we can easily fit the model on there. It's just about like how big of a batch size can you process. So, you could fit the whole thing on there and maybe do a batch size of like 4. But as soon as you try to go to a batch size of like 18, it'll just explode because you can't fit all of that into one of those small GPUs. So yeah. Does that answer your question?
Yes. Yeah, it does. So back of the envelope, we're looking at probably on the order of about a terabyte of resident memory that you're dealing with when you're going through the training process.
Yeah. Our speech recognition models, they're like a few hundred million, let's just say like 500 million parameters. And they are trained on like tens of millions of audio files, like unique audio files. Each of those audio files, you're getting the input to the speech recognition models. It's either like the raw audio, which is what you see with wave to vec, or it's something called MFCC values or spectrograms. Spectrograms are, some of the more common feature types that are used as the input to your speech recognition models. But those spectrograms, you're talking like, each data point is like 160 dimensions. So it's high dimensional, like sequential data that you're sending in. So the models they're so compute intense. Like our real-time transcription model is way less compute intense, and you can run it on your MacBook Pro and get pretty good accuracy, but it's not as robust or accurate as our like asynchronous batch transcription model that is what we transcribe like podcasts and video recordings and stuff with, because we're trying to maximize accuracy. So it's really just a trade-off of like how accurate do you want to make your model. But with our company, we're trying to build just very generalizable, accurate models. And a great parallel really is like GPT-3. I mean, that thing is enormous, but it's so good at so many different tasks. It's just this giant language model that was trained on like a crazy amount of data. And you end up with this very performant, generalized model that can handle a lot of different tasks.
In terms of the sort of trade-off of accuracy versus model size, you mentioned it a little bit that it's, a nonlinear relationship, but what are some of the observations that you've made as you've iterated on the capabilities of what you're building at Assembly in terms of the utility of having a larger model for greater accuracy versus having a smaller model for ease of deployment and lifecycle management?
It really is about, for us, making sure we're solving our customers' needs. So, because for us, since it's not just a pure research project, we're actually trying to build an API that customers are getting a lot of value from, that's solving a business case for customers. It has to be accurate enough for customers to be able to go build what they're trying to build or do what they're trying to do. And so there's definitely trade-offs at a certain point. Like if I were to say to a customer, hey, 91% accuracy costs $1, but like 93% accuracy costs like $10, they probably wouldn't care enough to pay that much more, like 10x. So for us, it's, we could make our models, much, much bigger, and it would just be much, much more expensive, both to train and both to serve. And you do get diminishing returns as you increase model size and as you increase the amount of data you're training on, because these models only have like so much modeling power. You can't just make like a 10 billion parameter ASR model and like, boom, it's human level. Like there's going to have to be better loss functions and neural network architectures invented before ASR can be human level. So at a certain point, there's diminishing returns, and you do have to make that decision. And a great example is right now, we're launching the next version of our ASR model in about like a week and a half. And as part of that pipeline, like you can either use a simple like LSTM neural network, like a LSTM language model, or you can use a like more traditional classical like n-gram language model. And the LSTM is way more compute intense and improves accuracy by like 0.1% compared to the n-gram language model, which is like much, much faster, much, much easier to train and serve. And it's like a 0.1% difference. So if we were trying to write a paper to just maximize accuracy, we would probably just, do everything we can to maximize accuracy, even if it was just like 0.1% improvement. But because we're trying to deploy this in production at a cost that is reasonable for our customers and at a cost that's also manageable for us as the company that's hosting it, we just look at some of these trade-offs between, okay, this is more compute intense, but it's only like a small improvement in accuracy compared to some other model that might be much more performant, but like close enough to a different model. in terms of performance, accuracy performance.
In terms of the sort of cost versus reward aspect of dealing with these large models, particularly as a startup, as you mentioned, and some of the sort of both opportunity and financial cost that goes into building these models and doing the research and iterating on them before you're able to ship a new product and feature, what are some of the useful lessons that you've learned and lessons that you would share with other startup founders about some of the ways to be able to manage some of those outlays to be able to remain viable as a company and be able to leverage some of these more advanced machine learning capabilities as the sort of core element of your product?
One of the first lessons that is obvious in hindsight, but I think a lot of startups are just focused on like shipping and moving fast, so they miss, is you've got to really know like what metric are you trying to optimize, which is different from, the objective function of your neural network, right? So I'm not talking like minimize loss. I'm talking like, for speech recognition, it's the word error rate, right? So if you're going to start any machine learning project that you're going to start, you should first, before you do any modeling or anything, like come up with some benchmark data sets, figure out what the current state of the art is on those benchmark data sets. And like, that's what you should be working towards. Because if you just look at papers, a lot of the data sets that are used in papers they're in like a laboratory setting, right? So it's completely irrelevant for real world data. Great examples like speech recognition. Most of the data sets that are used are from a data set called LibreSpeech, which is like very clean audio, people speaking like, the microphone's like in their mouth. So it's like very near field audio, very clean. They're probably in like a sound booth or something, compared to a phone call in the real world where there's like wind and noise and the person's like going back and forth from their phone and there's like people talking in the background and the sample rate sucks and there's all this like downsampling happening in the network infrastructure to reduce like the telephony infrastructure's costs, which is just compressing the audio data further and further. So to any machine learning company, basically it's like you really should first start by saying, let's create a really good set of benchmark data sets, and then through either humans or from comparable products on the market, let's figure out what is the level of accuracy. One, what is the metric we care about? And then two, like how does the industry today perform on that metric against those data sets? And it's different from like a validation or test set. It's a completely different set of data sets that you should have. And that is really where companies should start, is with that. And then once you start modeling, luckily, a lot of the frameworks have gotten better over time. So like PyTorch has really good distributed training built into it now that actually is pretty good compared to like a couple of years ago, when we were training our models with TensorFlow and hooking up Horovod to get good performance with distributed training. It was just harder. So you can do pretty well now, and there's access to faster GPUs like the V100s, and I think Google Cloud has the A100 GPUs that you can rent, although it's like, I think $25 an hour or something. So you're definitely in a better spot today as a startup, but another like major lesson is, you really just shouldn't train models on big cloud infrastructure like AWS or Google Cloud. It's just like stupid expensive. We have worked with this one cloud, I don't even want to say cloud provider, like this like small company that we lease like dedicated GPU clusters from. So they're on like 24/7. We pay monthly fees for them. And we have like hundreds of V100 GPUs that are just always available for us to train on. And it's like a sixth of what it would cost if we were trying to do that with AWS. And then there's a lot of programs that big clouds do offer for startups. Like you can get like $50,000 in like EC2 credits or $10,000 in EC2 credits. So like maybe just start with like a big cloud and like use up your credits and then kind of switch to a dedicated hosting provider where you can pay, a couple $1,000 a month and you can actually have like GPUs. You get better performance and the costs are lower. And there's always the option of actually buying the hardware yourself. There's a really cool company, I think it's called Lambda Labs, where you can like buy training rigs. But then there's a question of, where you plug that thing in, because the electricity draw is huge, and we can SSH into some of our instances and you can like look at the GPU temperature and it's like, like 40 or 50 degrees Celsius, like all the time. So if you get like a 6 or 8 GPU rig and you plug that into your house, I don't think it would work. I think it would probably trip your whatever it is. And your energy bill would be really high if it didn't. Your house would also probably be very hot.
I was going to say, you wouldn't have to pay for heat in the winter.
Yeah. It could be an option, A way to heat up your house. Yeah.
I think I might have actually seen a startup a while ago that was trying to sell like mini compute nodes that they would distribute to people's houses, and like they would pay you to run it, and it would provide heat to your house.
Yeah, I think I saw that too. That would be amazing.
Yeah. I don't know if it's a joke or...
Yeah. I think it was real. But yeah, it's just like, if you're going to try to do it at any type of scale, it is really hard to pull off hosting yourself. And then you have to have someone that's going and like restarting these servers all the time if they go down or something. So it is easier to just rent machines, but you definitely can't do it with big clouds. It's just way too expensive.
Digging more into some of the specifics of the actual model development process, particularly as far as the sort of feature extraction and feature identification for understanding what to use as the inputs to your model. I'm wondering if you can talk through some of the sort of techniques that you use and attributes that you focus on as far as the feature definitions for inputs to your models from the source audio data that you're using.
Yeah, so some of the newer model architectures like Wave to Vec, they're just modeling the raw audio data, which makes more sense because the more traditional feature extraction methods are getting those what are called MFCC values or spectrograms off the audio data, but those are human crafted features, which then kind of starts to feel more like classical machine learning, where you have like someone designing features and building features. So in theory, intuitively, it's better to just like feed the raw data to the neural network and then have it figure out what the features are that are important. And that really is, I think, kind of where the future is going. Yeah, those are the three main options. It's like spectrograms, MFCC values, or just raw audio data. The raw audio data is for sure the coolest option. Yeah, you're just letting the neural network, like if you throw a couple convolutional layers at the top of your network, you're just letting those basically turn into feature extraction layers off the raw audio data. And then they're developing some abstraction that's turning into a feature set that is getting fed into like some transformer layers or RNN layers or something. But those are some of the main options.
As far as the just lifecycle management of the ASR models that you're building at Assembly, can you just talk through some of the sort of complexities that go into monitoring and identifying model drift and figuring out when you need to retrain and redeploy the models and just that overall operations aspect of it?
Yeah, there's a lot that goes into that. Before we push anything into production, we do just a ton of QA, because we really want to make sure that the models are performing well on tons of different types of data, are going to perform well for customers. It's going to absolutely perform better than the current version that was in production if we're going to make a switch. So the first step is just doing a ton of QA so that there's a lot of confidence that, okay, this new model we're pushing into production is going to be better. And so we have a bunch of data sets that we run our models against. We look at the accuracy numbers. We look at a bunch of metrics to make sure that they're performing better across the board. And then once we push them into production, usually the things that come up are like DevOps related things. Like, you realize, okay, for some reason, you actually can't have a batch size of like 16. You need to just use a batch size of 14. Or there was some setting that was misconfigured in terms of the sequence lengths that you're passing into models, and the model explodes if the sequence length is too high. So there's like edge cases in the actual code that have to be smoothed out when the model profile changes. But there's two different types of model updates. Like one is the nice and easy type, which is just, you're just updating the model file. Like you just have new weights basically. Like it's the same architecture and everything. It's just the weights are better now. And that's what we call just like a drop in. And that's usually pretty safe if all the accuracy metrics are cleared. Because from an infrastructure and DevOps perspective, like you're just pointing, to a different file, same architecture, just different weights. So it's usually pretty safe. Where it gets more gnarly is if you have like a new architecture. So we're actually going through this right now. Like most of our infrastructure is built around our like V6 ASR model, which is like a really large CTC model. And we're transitioning now to our V8 model. And V8 is a completely different architecture. So the whole pipeline has to change. There's like a lot of infrastructure that has to change. And there's a lot of actual, programming and DevOps that goes into it. And that's a beast versus just dropping in a model file. So on one side, there's like a quality perspective, like does the accuracy of the model kind of meet what we need it to meet? And then on the other side, it's, okay, Are we just updating the weights of something that's already in production, or are we shipping a new model that behaves completely differently and infrastructure needs to change completely, in which case the engineers are usually less happy and they need to they need to roll up their sleeves and get to work.
As far as just the overall space of ASR and some of the ongoing research that's going on there, I'm wondering what are some of the areas of activity and exploration and some of the items on your wish list that you would like to be able to push into production, but that are still too intractable or impractical to be able to productionize?
I think the future of ASR is going to be around like unsupervised training. Is very similar to like what you're seeing with GPT-3, and like you have these models that are very large that are trained on lots of unsupervised data, and then you're just fine tuning them for specific tasks or for specific languages. I won't say too much there, but that's like a really interesting area of research that we're actively looking into, and the results are like really promising.
To your point of being able to extend some of these NLP models to other languages, I'm wondering what are some of the capabilities that you're looking towards as far as being able to support other languages from an ASR perspective?
Transfer learning and unsupervised training, it makes shipping other languages so easy because you can, train a model on like 50,000 hours or 100,000 hours of unlabeled like Spanish data, and then just fine tune it on like 100 hours of labeled Spanish data, and you're going to get like pretty good results. And so that's a pretty clever way to quickly spin up new languages. It sounds simple, but it's like the part of training a model on like 100,000 hours of unlabeled like Spanish data that's the challenging part. And you need the infrastructure and compute and know how to do that. But once you have that, the fine tuning to pump out new languages is actually pretty simple and works pretty well.
In terms of your experience of using ASR technologies and building the models and some of the ways that you're seeing it used either with the assembly product or in other avenues of ASR capabilities, what are some of the most interesting or innovative or unexpected ways that you've seen those capabilities used?
So in general, you are just seeing a ton of new use cases appear that are leveraging transcription. And they're either using transcripts for simple use cases like accessibility features, closed captions, or readable voicemails, like visual voicemail. And then you're also seeing a lot of applications that are being built on top of transcription. So they're using the transcriptions as inputs to summarization models or to figure out like topics that are spoken within an audio file or video file. And those are really exciting use cases that we're seeing a lot more of. The macro trends is that one, there are now APIs that make this technology accessible. This is actually a very new thing. Like 5 years ago, there were not APIs that you could just go get accurate ASR from. You had to go beg Nuance for license and pay them tons of money and deal with their software. But now you can come to APIs like Assembly and you can just get, as a developer, without having to even put in a credit card, access to state-of-the-art speech recognition technology. And the accuracy is a lot better as well. And if you do end up deploying something into production, the cost has come way down. And so those three macro trends, like accessibility, accuracy, and cost coming down, are driving a lot of innovation in this space. And we're just seeing so many applications launch every day that are making use of audio or video and the transcripts of those audio or video files.
In your own experience of working in the space of ASR and building a business around that technology, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
Yeah, I think it goes back to some of those lessons learned around training machine learning models as a startup that we just, learned in the early days of the company, in terms of like, really making sure as a machine learning company, as a machine learning startup, that you have a good compass to use. So that you have like good metrics that you're tracking on your model's performance, and you have good benchmark data sets that are comprised of real world data and not just, laboratory or research data sets. You really have to be able to know and measure, how your models are performing on real world data. And you have to have an acute understanding of that so that like which direction to move in. You need a good compass. And then the other is really just about that speed and cost trade-off. I think ML startups need to recognize that you just can't move as quickly in the early days as a traditional startup, because you can't just ship a feature overnight. It might take you a couple weeks to get more data together. It might take you a couple weeks to train your model. It might take you like a week or two to deploy it. And that feels slow for startups because startups, you want to be able to like get customer feedback overnight, ship improvements, and then, rinse and repeat. But as an ML startup, it's kind of more similar to starting like a hardware company where, you just can't iterate as quick as a pure software company because you have this huge data science or machine learning component of your business that is at the core of what you do.
As you continue to build out the assembly product and continue to invest in research for ASR, I'm wondering what are some of the overall trends in the research or in industry that you're keeping an eye on and thinking about as far as how to factor that into your product or interesting areas to explore?
The unsupervised pre-training is a really interesting area, like across the board right now. I think, GPT-3 is like a great demonstration of the capabilities that can have. Wave to Vec for ASR has shown a lot of progress for unsupervised pre-training, but that is a really exciting area. There's limitless unlabeled audio and video data on the internet. And, being able to tap into more of that data, train and build bigger models that can learn from all that data is a really exciting area right now.
Are there any other aspects of the ASR space and the work that you're doing at Assembly to help sort of drive the industry forward and build research and just manage the overall model development and deployment and lifecycle management process that we didn't discuss yet that you'd like to cover before we close out the show?
No, I think we talked about most things, to be honest. We got a good breadth of topics that we covered. So it's challenging stuff, but it's fun and it's fun engineering problems to work on, really. So, while there's like cons to all this as a startup, it is a way to attract good engineering talent because there are hard problems that good engineers want to work on.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. This week, I'm going to choose a movie that I just watched recently called The Hitman's Wife's Bodyguard. So it's a follow-up to The Hitman's Bodyguard, both of which are just hilarious action movies. Ryan Reynolds is always entertaining to watch, and his interaction with Samuel L. Jackson. So just fun, mindless entertainment if you're looking for something to watch this weekend. So definitely recommend that. And so with that, I'll pass it to you, Dylan. Do you have any picks this week?
I'll have to watch that. I scrolled over that and I didn't hit enter, but maybe I'll go back. Yeah, the Inspiration 4 documentary on Netflix, actually, I think they're launching tonight in 4 hours, is really cool. People should check that out. And you should also watch the launch tonight that's happening in 4 hours. I guess by the time this is published, they will have already gone up and come back down. So you and I should go watch the launch tonight. Yeah.
All right. Well, thank you very much for taking the time today to join me and share the work that you're doing in the ASR space and some of the complexities and challenges that are involved and some of the upcoming capabilities that people can look forward to. So definitely a very interesting problem domain. So I appreciate all the time and effort that you and your business are putting into it. And I hope you enjoy the rest of your day.
Yeah. Thanks for having me on here. Really appreciate it.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.